Exponential models show up constantly on the SAT. Bank accounts, populations, and quantities that change by a percent each time step. The key is to translate words into a starting value, a growth or decay factor, and an exponent on time. Once the form is correct, the rest is careful arithmetic and reading the units. The common SAT form is y equals a times 1 plus r raised to the t for growth, when r is written as a decimal rate. For decay, you often see y equals 8 times 1 minus r raised to the t, when the quantity shrinks by r each period. Here, a is the initial amount, r is the fractional change per period, and a to t counts how many periods passed. The graph of growth bends upward when the base is greater than 1. Decay bends towards 0 when the base is between 0 and 1. Decay looks like a curve that falls quickly at first, then levels off as the remaining amount gets smaller. Example 1. Easy. Suppose you start with $1,000 and it grows 5% each year for 3 years. 5% as a decimal is 0.05, so the multiplier each year is 1 plus 0.05, which is 1.05. The model is y equals 1,000 times 1.05 to the power t with t in years. After 3 years, substitute t equals 3. You multiply 1,000 by 1.05 cubed. That is about $1,158.63 if you round to the nearest cent. Example 2, medium. A population doubles every 10 years. Write an exponential model with t in years. Doubling means the factor per 10 years is 2. So if t is years, then the number of 10-year periods is t divided by 10. A clean form is p of t equals p0 times 2 to the power t over 10, where p0 is the starting population. You could also write this using 1 plus r, but doubling is easiest as base 2 with a rescaled exponent. The graph climbs slowly at first, then shoots up as each doubling stacks on the last one. Example 3, harder. A radioactive sample has a half-life of 8 hours. Model the mass after t hours. Each half-life multiplies the mass by 1/2 in one half-life period you multiply by 1/2 1. If t is hours and the half-life is 8 hours, the number of half-lives is t divided by 8. For instance, after 24 hours you have 3 half-lives, so you multiply the start by 1/2 cubed. The decay graph falls steeply early, then flattens, which matches how half-life problems behave. Common mistake, using r alone as the multiplier instead of 1 plus r or 1 minus r. If a balance grows 8% per year, you multiply by 1.08, not by 0.08. Another trap is mixing up the time unit. Months versus years must match the rate you are given. SAT pro tip. When a quantity increases by x%, multiply by 1 plus x over 100. For a decrease by p%, multiply by 1 minus p over 100 as long as that stays positive. Doubling and half-life are vocabulary shortcuts. Translate them into base 2 before you panic. Recap, growth often looks like a times 1 plus r to the t. Decay like a times 1 minus r to the t. Second, rewrite doubling or half-life as repeated factors with t scaled to the correct period. Third, never confuse the rate r with the full multiplier 1 plus r. Practice more on NovaMaths.